Great, let's get going. Okay, my name is Runar. I'm going to be talking about category theory from first principles, right from the beginning. Okay, how many people are familiar with category theory? Like, yeah, a good half. All right. How many people could tell me what a category is? Like half of those people. Great. Awesome. So, well, I'm just going to start from the very beginning. So, everybody familiar with functions? Yeah, we're good. Okay, cool. We're good with functions. So let's talk about the API of functions. Like, what is the programming model of functions? Okay, so like in Scala, for instance, we have a function, call it f, and it goes from the type A to the type B. And we have a function g that goes from the type b to the function c. Then we also have a function g compose f that goes from the type A to the type C. All right, so this is one of the things you can do with functions. In fact, this is like the only thing you can do with functions. So functions compose. And they compose in an associative way. That is, if I say g compose, or let's actually want to flip these just for so I don't confuse myself. This is g, this is f, and that's g. Great. So now if I say f compose g compose h, compose h, like, well, given that h goes from C to some other type, this will always work. And like if I put the parens here, or if I put the parens here, that should mean the same thing. Right? It doesn't matter which way I associate this. If I compose this function with that one, or this function with that one, like, doesn't matter. You obviously can't flip them, because then the types won't line up. Like, you can't say g compose f, because the types are incorrect. But you can compose them in any order. Great, so it's associative. All right, so another thing about functions is that for every type A, there is a function of type A to A called identity. Let's call that ID. That's ID of A. And that has the implementation, lambda of x goes to x. So it just returns its argument. And the property that this function has with regard to composition is that it's an identity for the composition. That is, it's a unit. So f compose identity is the same thing as identity compose f. And that's the same thing as f. Right? So the identity function does nothing with regard to composition. OK, so that's the sort of the abstract API of functions. They go from types to types. They compose in an associative way. There's an identity for every type that does nothing. Great? Cool. Let's now go to the abstract. Let's talk about categories. All right, so a category, so this is what a category is. A category consists of some objects, some arrows between those objects, and there's a composition of the arrows, which is associative and has an identity, just like this. So this is a category, but there are lots of other categories that behave the same way in the abstract. All right, so this is category theory. All right, so if you didn't know category theory before, now you do. Thank you. Great, awesome. Everybody can go home. I mean, you know, this is really all of it, and it has cool implications that we'll explore. Great. Let's look at some more examples of categories. Okay, let's look at. So we're looking at the Scala category here, but let's look at how Scala is a category in a different way. So something that doesn't involve functions. So in this category, so the category we were talking about before, I'm going to push that onto the stack. That category is called, let's call that category Scala. In the literature, it's often just called set. That is, it's a category of sets and functions between sets. But we want to talk about types, Scala types, and functions between Scala types. But so to a first approximation, Scala types are sets of values, right? So let's talk about how Scala is a category in a different way. So then I'm going to talk about a category that I'm going to call Scala sub. So in that category, the objects, so now we just got to go to our definition of category, and we've got to provide these things in order to get a category. This is the data structure that we need. So let's instantiate that data structure here. The objects in this category are Scala types. Okay? The arrows in this category are as follows. So whereas in this category here, the arrows were functions between types, in this category, the arrows are subtype relationships. So there is an arrow from A to B. And we'll write that like this. Exactly when A is a subtype of B. All right? So this is how we construct an arrow in this category. If A is a subtype of B, there's an arrow. Now you'll note that if A is a subtype of B and B is a subtype of C, then A is certainly a subtype of C as well. Right? So arrows compose. Yeah? So this is the composition on the arrows that we can reason from here to here. Right? So if we call this arrow F and we call this arrow G, then we can call this arrow G compose F. Sweet? You'll also note that in this category, there's at most one arrow between any two objects. Right, so these arrows are unique. That is, if you say that A is a subtype of B and you say it again, you can't say it in a different way. It's A is a subtype of B in a unique way. Right? Okay, so and also then for every type, like we need associativity, right? So associativity is the transitivity relation. So if we have A being a subtype of A being a subtype of B, which is a subtype of C, we can reason that C is a supertype of A by simply, saying like, well, we'll reason this way first. A is a subtype of B, all right? And since A is a subtype of B and B is a subtype of C, then A is definitely a subtype of C. But we can also reason the other way. We can say, well, B is a subtype of C, and then A is a subtype of B, therefore A is a subtype of C. So composition on the arrows is associative here. Everybody cool with this? Great. And we need the identity. for every type A, there is an identity arrow, which is just the fact that every type is a subtype of itself. And that doesn't do anything. Like, it doesn't add any additional information in this composition. We said A is a subtype of A, and A is a subtype of B, therefore A is a subtype of B. Like, the identity doesn't add anything. Great. OK, so now we have 2 examples of categories under our belt here. Pretty cool. Let's look at some more examples. So what I'm basically going to do is just give you lots of examples of categories, so you can sort of start to understand what all of this is for. So that was a category where between any 2 objects there was at most 1 arrow, and actually such a category is called a poset. And we can actually do this in general, that whenever we have some set, we have some poset. So a poset is a partially ordered set. So if we have a set that has, it has some values in it, right? Some type, and it has a relationship like less than or equal to. So for any given for any 2 objects in the set, we can ask, well, is A less than or equal to B? And if it is, there's an arrow from A to B. Okay, so the Scala subtype, the Scala type system forms a poset in this way. Great. And we can do this in general. Like, for instance, we can say int is a category like this, where there's an arrow from A to B, like the integer A to the integer B, exactly when A is less than or equal to B. And it works exactly the same way as we did before. Like, every integer, is less than or equal to itself. Right? That's the identity. And it composes in the same way as we did with Scala sub. Great. So that's a poset category. And so a poset, we can give a precise definition of what a poset is in category theory terms. So a poset is a category with at most 1 arrow between or from A to B for any 2 objects A and B. Cool. So we can start to give purely category theoretic definitions just given this stuff. People familiar with monoids? Anyone not familiar with monoids? Wow, that's awesome. Everybody's like, yeah, monoids, great. Cool. OK, so what is a monoid? A monoid, we can say, is a set. Right? It's a trait, monoid. We give it some set, M, some type, right? And it has, well, it has append, and it has the 0 type M, and append goes from M and M to M. Yeah? And so in a monoid, we can compose the values. And composition is associative on the values. And there's an identity, a 0, for composition. This is looking like a category, right? And in fact, a monoid is a category. A monoid, and we can give that in a purely category theoretic terms. A monoid is a category with 1 object. OK? So how does that work out? So we can think of the values of type M as being arrows. And so they are just arrows from that 1 object to itself. They go from this object to itself. So this might be, let's say this is integer. and this might be the arrow 1. And then this might be the arrow 2, say. And that's going to be the same as 1 and then composed with 1. OK? And so we can build up the natural numbers that way. Oh, and there's going to be an identity arrow, which is 0. And so we can build up the integers by composing arrows this way, where we say, like, oh, this is 1, and this is 4, and this is 6, right? And this whole thing is the arrow 11. Yeah, question?
So when you say it has one object, translating it into Scala terms, that mean it operates over like one type?
No. So the object in here is not really a type. So and these arrows are not functions. Okay? So we've gone from, so we're no longer in this category. This is not the category we're in. We are in this category here, the monoid M. Okay? Where the arrows are the values of type M, and the object is just some arbitrary object. The only reason that this object exists, we can just erase it. The only reason it exists is to say that all of these arrows are compatible. That is, we can compose any 2 arrows. Right? Okay. And the directionality of the arrow, it's saying that this, while this is associative and all of that, it's not commutative. So the direction matters. For instance, if these were strings, this were like foo, and then bar, and baz, we can't flip the order. The direction of the arrow matters. It's foo, bar, baz, not foo, baz, bar. Right? Cool. So a monoid is a category with one object. And this is a precise specification of what monoid is in category theory terms. So if you know what a category is, and then you say a category with one object is a monoid, now you know what a monoid is. Cool?
The one object is the monoid?
Yeah. The one object, I mean, the whole category is the monoid.
Oh.
Right.
What is the object?
That is a meaningless question. Like, what? No, I mean, the object has no structure, right? Other than the fact that it has arrows that are tied to it. That is all of it. Yeah.
So it is the beginning of the arrows? That's the point?
It's both the beginning and the end of the arrows. Yeah. It ties all of these arrows. It simply means that all of these arrows are compatible. You can compose any 2 of them because they go from that object to the same object. And so you can always go back to that object as many times as you want. So it means you can build all of the strings from arrows that are all tied to this one object. Yeah.
It might not be helpful if you mention in the base definitions of category for your composition that every time the arrows line up, there must be a composition.
Right.
Kind of gloss over that.
I did gloss over that. That's true. Yes. So in category theory, it's like if you have, I guess I started out by saying that if you have F that goes from A to B, and if you have G that goes from B to C, you always have G compose F that goes from A to C. Like this always exists and always works. And so what the monoid, and then the types, the objects have to be the same. In order for, like, this works only if and only if, and always if, the destination of F is the same as the source of G. Okay? So it's like we got A, B, and C, F and G, say, and this always exists and only if they agree on this object. So in a monoid, all of the arrows agree, sort of trivially. And therefore, we can take any 2 strings and compose them, because strings are monoids. Cool? So composition always works for any 2 M's. Now, let's look at a different category where this is not true. So maybe that will be a little illuminating. Well, we can look at, let's look at dominoes. Dominoes. All right. So in the game of dominoes, there are some objects. Let's call them 1 through 6, right? Like they could be oh, it's 0 through 6, I guess. Well, let's ignore that there are zeros because that has a special rule. So 1 through 6 in a sort of a simplified game of dominoes. That is, an end of a domino like this can have, between 1 and 6 dots on it. And for any 2 dominoes, if they agree on the dots, the number of dots on one side, they compose on that side. Cool? And they form a new domino, a longer domino, that you can keep composing on. Okay? So this is now a category where you don't have one object, you have 6. And so the arrows are not all compatible. They're only compatible when they agree on the ends. And there's an identity for every value, for every object. That is, the domino that doesn't change the end. Cool? So that's contrasted with the monoid, where there's only one object. Now there are 6. And so we have this sort of incompatibility. And so really, you can think of a category as a generalized monoid. Yeah? So it's just a category is like a monoid where you just have more capability, where not all the arrows, or where not all of the things that you can compose are compatible with one another. There are some rules of compatibility. Okay, like in the types have to be the same. In the dominoes, the number of dots has to be the same. In the poset, it has to be the same value. Yeah.
So in the case of like Scala set, where the objects are like types and the arrows are functions in
Yep.
Scala,
Yeah.
is it useful for me to think of that as like a category with like infinite objects, because I can just make an infinite amount of types and an infinite amount of arrows?
Yeah. Yeah. There's not a finite number of objects in that category, right?
And then one, I guess, other clarification about poset. So is Scala set that category where the objects are types and the arrows are functions? That doesn't form a poset?
Wait, sorry?
The category Scala set,
Yeah.
does that form a poset?
No. Because there is more than one arrow there can be more than one arrow from any one type A to another type B.
There are a lot of functions from string.
Yeah, a lot of functions from string to string, a lot of functions from.
Poset's kind of like a subcategory of Scala set, given that subtype gives you a function from A to B.
That's a great point. Yeah, you can go from here to here, like there's an embedding of this in here, right? Like you can look at a subtype relationship as a function where all the functions give you the identity function, right? So.
What's a subcategory?
Oh, so it's just like, so this has a number of objects, right?
Yeah.
And this thing has fewer objects, as it were. Sorry, arrows. This is a number of arrows, and this has fewer arrows, because like there's at most one here for any 2 types, but there's lots. And if you can go from here to here by simply saying, well, I'm just going to take the identity functions. Like if I have a subtype relationship like this, A is a subtype of B, I can say, well, I have a function from A to B, which is just the identity, right? Sorry? It's the identity on B, yeah. So. Right. Yeah, you just have to like upcast one of them to the larger type. And in fact, all of the arrows, if you go from here to here, you will get into a category where all of the arrows are identity arrows, right? And such a category is called a discrete category. Discrete category. All arrows are identity. Right, so then you just have some things, some objects, and the only arrows are the identity arrows. That's a category you can construct. And there are lots of little categories that you can construct like this. Like you can construct the category 1. The category 1 has one object, and it's a discrete category. It only has an identity arrow. This is a perfectly cromulent category. You can also have the category 2. The category 2 has two objects, and it has an arrow between them. And obviously, there's an identity arrow for both of these objects, and all of the arrows compose. And we call this category 2. And there's category 3 with 3 of them, and like it has one composite arrow, so it's like a triangle like this. And there's a 0 as well. This is a category with no objects at all, and no arrows between those objects. And that's a perfectly cromulent category as well, because we can just say, well, it has 0 objects, 0 arrows, and the composition works trivially, because we don't have any work to do. Cool. So we've done monoids. We've done like dominoes and stuff. Let's go higher up. So we were talking about embedding this category into this one via some kind of operation here, right? That's kind of weird, right? So what kind of thing is that? That kind of thing is a functor. So a functor say functor from category C, to D. We can say it's a functor f that goes from C to D, like this. And here's what it does. It maps every object in C to one object in D. And it maps every arrow as well. So every arrow in C to an arrow in D in such a way that the composition still works. So if we say F on some object, on some arrow F, and we compose that with F of some other arrow G, both of these arrows are in C, and F of those arrows are in D, that should be the same thing as F of F composed with G. Like the composition is preserved. And also, the identity should be preserved. F of the identity should be the identity. Yeah? In fact, this forms a category. So we can talk about a category of categories. Category of categories. What's that?
I want to give an example of
OK, an example of a functor. Let's do that. OK, this is an example of a functor where I was embedding Scala sub, the Scala set. Can we do another one? Where we, yeah. So an endofunctor goes from some category C to itself. So an endofunctor on C is a functor from C to C. Endo means within. So it's within the category C. So it maps every object in C to another object in C, or the same one. And it maps every arrow in C to another arrow in C, or the same one. In such a way that this works. So an example in Scala is list. Okay, list is an endofunctor in Scala. So list takes every type t to the type list of t, right? Like we can write it. We could write it like this. List is a type level thing that goes from the type t to the type list of t. It's a type constructor like this. So it maps every object in Scala to another. I mean, every type in Scala to another type in Scala. It maps every arrow in Scala to another arrow in Scala. So it maps the arrow f, takes that to mapf. So underscore dot mapf. Right? That is, we go from A to B to list of A to list of B. Right? And it works out that if we first map F over a list and then map G over a list, it has the same result as mapping the composite function fg over the list. Yep.
Like my intuition tells me that looks kind of like pure from like a T. So like a type constructor which takes a T and turns it into a F of T.
Yeah. Are you telling me that list is a type level monad?
I don't know.
I think you're right. But yeah, I mean that would be a cool thing to explore. Like you could definitely take a look at that. Okay, where were we with this?
One other weird thing is that endofunctor has like one object, so it's kind of like a monoid.
Yeah. So this endofunctor thing is just operating on one category. Yeah. So you can think of this as being like an object in this kind of category, where, or in a category where like C is the only object.
Consists of all endofunctors, because you can compose them.
Sorry, what?
The monoid that you were talking about consists of all possible endofunctors because you can compose them.
Exactly. Yes. It's the monoid of all endofunctors. Yeah. So that's good. That is, it's the monoid where the only object is the category C, and then all of the arrows are the
Possible
endofunctors in C. Yes. In fact, we have categories of endofunctors, which we can get to. But let's talk about the category of categories. Start with that. So sort of like to understand what functor sort of means in terms of category theory, we can talk about that category cat of categories. So the objects in here, objects are categories. The arrows are functors. That is, they are mappings from categories to categories that preserve the structure of the category. That is, they preserve composition and identities on the arrows. Cool. And what is a composition in this thing? Composition on the arrows. If we have a functor f that goes from C to D, and we have a functor g that goes from D to E, then we have a functor, f g like this. Oh, sorry, gf. G f like that. So the composite functor that goes from C to E. Right. And composition is associative. That is, if you have H out here, doesn't matter whether you compose F and G first or H and G first. And there's an identity functor, which is just, type, identity functor for every category. So that takes the category C to the category C, preserving everything. Identity on C goes from C to C. Right. So it just takes all the objects to themselves and all of the categories. Sorry, it takes all of the objects in the category to themselves and all the arrows in the category to themselves. Cool. Yeah, we were talking about categories of endofunctors, right? OK, let's talk about that category as well. Do I have time, by the way?
The home audience has about 11 minutes of memory left.
OK, cool.
I think we're welcome to keep the room longer.
All right. I mean, I think the panel is in about 10 minutes, so we'll wrap this up soon. OK, for any category C, we have a category of endofunctors in C. Let's call that endo C, I guess. Where the objects are functors from C to C, so endofunctors in C. The arrows are transformations between functors. They are natural transformations. Natural transformations. OK? What does that mean? So a natural transformation means that if you apply, now I'm getting into the weeds here. So natural transformation goes from a functor f to the functor g, say. So for two functors, so this is a natural transformation from f to g. We can do the squiggly arrow thing here, like we do in Scala sometimes. So it goes from f to g. And in Scala, when we're working with endofunctors in Scala and natural transformations between them, we talk about this being a function that, given some type A, takes you from, I guess I'm going to use like the Dottie syntax here. Given the type A, it takes you from f of A to g of A. Cool? So that's your work for any given type. Takes you from an f full of A's to a g full of A's. And the rule here is that how do I express this as a homomorphism law? If you have
You map from A to B.
Sorry? Oh, yeah, if you have a map from A to B, great. So these are some objects in C, a map from A to B. Then you can do f of A. If you have an f of A and an f of B, you should be able to do, sorry, wait.
You lift that to f of A to f of B and also to g of A to g of B.
Right. So I have, fuck. Do you want to? I'm just totally blanking here on this. Do you want to help me out here?
Sure.
Yeah, help me out. I'm thinking in terms of homomorphism law.
Well, I'm not.
OK, that's good.
So I'm just saying I've got g of A
Yep.
to g of B also.
Right.
Right. Now, but I have f of A to g of A,
Right.
and I have f of B to g of B.
Right. And that should work. Great. That's it.
So then this should commute.
Exactly. Thank you. That's what I was getting at. Right. So it's that.
You start with a function from A to B, and you lift it.
Right. So you start with a function from A to B, call that f, and then this is our natural transformation, call that h here, and then this is f of f for our functor f, and this is g of f for our functor g. And this is saying that doing this composed, h composed with g of f is the same as doing f of f composed with h. Like these two paths through this diagram are the same, and we say that the diagram commutes. Yep.
So in that diagram, which ones are the objects and which ones are the arrows? Like, are the natural transformations arrows in the same way that, like, the lift from or the function from f of, or the arrow from f of a to f of b is an arrow? Like, are they the same notion of an arrow?
So these are objects in the category C, right? So these are all objects in this category here, and for an arrow in the category of endofunctors on C to be, a natural transformation, it needs to satisfy this kind of law that operates on the objects of the underlying functor. Underlying category.
To be super clear, like list.head option is an example of it.
Yeah, list.head option is one of these. And in general, I want to say that the arrows, I want to introduce this notion here. The arrows here should be homomorphisms. And so what does that mean? So for here, for set, it just means they're functions. That doesn't add anything additional. But if we're talking about, say, a category of monoids, say the category mon of monoids. So the objects are monoids, and the arrows are functions, just like in here. But they're special kinds of functions because now we're not in a category of all sets. We're in the category of monoids. And so we have to talk about what's called monoid homomorphism. Monoid homomorphism. And that's just a function, but it has to obey this kind of law, which says, so if we have an arrow in this category, let's call it h, it should hold that h of x composed with y should be the same as h of x composed with h of y. Right? So in order for a function to be an honest to goodness arrow in this category of monoids, it needs to obey this kind of law. It has to preserve the monoid structure. Okay, so for sets, that's not very interesting. Like set homomorphisms are just functions, but monoid homomorphisms are functions with this additional property. And you'll note that this is the same as the functor law, that map f composed G should be the same as map f compose map G, right? So this looks like the functor law, and that's not a coincidence, because in the category of endofunctors, the arrows are category homomorphisms. No, sorry, in the category categories, the arrows are category homomorphisms, which are functors. Cool? And what's an example of a monoid homomorphism? For instance, string length. So underscore dot length goes from the monoid for strings to the monoid for ints in such a way that taking the length of the composite string xy is the same as taking the length of x and adding that to the length of y, right? And there are lots and lots of examples like this. If you're in a Boolean algebra, for instance, the monoid is like Boolean with and. you can go to the other one, Boolean with or, through not. So not x and y is not x or not y. And that works the other way around as well. So that, the monoid homomorphism not is a monoid isomorphism. Because it goes both ways. Anyway, I think we'll just stop there. We're out of time. Thank you.